All right, so we're continuing with class number 4, and here's some additional examples from the textbook by a man named Cengel. It will be the same author as your fluid mechanics textbook when you take fluid mechanics. So you got that going for you, which is nice. All right, so we want to determine the internal energy of water at 20 degrees psi and 400 degrees Fahrenheit. Truth is, we haven't been doing internal energy yet, but we can still look it up. We're just going to mess around with the tables, so let's just go ahead and do that. So we need to have the U.S. America tables. So that's in Appendix F. If you're looking for Appendix F, and I have it tabbed. And we want 20 psi and 400. So let's first look at 20 psi. And this one does not have the saturated tables that are indexed by pressure, so you would want to look down and find pressure. There you go. Somewhere around 230 degrees is what the saturation temperature is, and we have a much higher temperature of 400 degrees, therefore it must be superheated. And you really want to do that kind of thing each time to check that you're, hey, should we use a superheated or not use a superheated? What is the state of this? So we get to we need superheated tables, and we need 20 psi, right? So look at there, 20 psi, and what was he say? The temperature had to be 400, right? So there is the here's the specific volume, and here is there. So that's all we had to do. And we can find out that it's 1,145.06 BTUs, which is a British thermal unit. Right, it's a form of heat, or the measure of heat in the old-fashioned style. But there it is, right there, per pound mass, which is also a weird unit that's very hinky towards thermodynamics. But we're stuck with it, so we got to get used to it. I'm not saying I like it, but I don't hate it. Just don't, I don't hate it. So this is what we did. We're going to keep track of that, write it down. We had 400 degrees Fahrenheit. We found, this doesn't look like the thing we did at all. What did we do? Oh, I went the other direction. Okay, so what I had done before was I went to 20 and I saw what the temperature was. Well, you go to the temperature and you can see what the pressure is. And you can see that the P sat for 400 degrees. We'll see. That's where if you wanted it to be saturated steam, here's the pressure that would go along, 347.08, which is a lot more than 20. Therefore, you can be pretty certain that it is superheated steam. And so, and we go, therefore, superheated steam. I guess maybe we could go that this is, maybe we say that this is greater than 20. I'm very tired, so I'm going to get loopy here. I know, you're going to say, how are you going to tell? So that's there, so therefore superheated. So we're going to go to table F.7.2 and find at, actually we're using the pressure first, right? Because it is kind of indexed first by pressure, because it's the little things in the top right here. Each one of these tables is by 20, and then it's indexed by there. So there, so we'll go with the we will find so at T is equal to 400 degrees Fahrenheit. You can find little u for that is going to be 1,145.06. That's a lot of sig figs. BTUs per pound mass. That's only 4 minutes. So let's continue to the next example in here. And this one does require an interpolation. And now we're back into good old SI units. And it's to determine the temperature of the water at a state where the pressure is 0.5 megapascals, which is the same as 500 kilopascals. And the enthalpy, which we haven't used yet, but this is a very common thing to do. Enthalpy is a very common important parameter. You could think of a lot of heat in terms of a change in enthalpy. So that's like a really important thing. And so we're going to go ahead and look that up. So the given was 500 kilopascals and 2,890 kilojoules per kilogram. So back to, and it's nice to have these tabbed. These tabbed right here. First off, what you want to do is go to the first one and find for that pressure. Well, no, go to the second one. It's a lot easier to do with the second one. This is indexed. And on the front page, we indexed by, what was the pressure again? Pressure was 500, right? So sure enough, 500 right here. And now the enthalpy is going to be on the second page, right? Because you get specific volume and internal energy on this page. You have enthalpy and entropy over here. So we're going to come all the way down and let's look at the enthalpy in the saturated vapor. If it's higher than this, it's going to be superheated. So here you go, 200, and we have 2,706.6. And what did we say we wanted to have? We had more than that. Therefore, it is going to be saturated. Superheated, sorry. So, table, what is this? B.1.2 at 400, P equals 500 kPa. Hg is equal to, I just had it, 2706, is that right? 2706. Kilojoules per kilogram is what the SI units are for enthalpy. And so we go over to table B 1.3. And take a look at 400. And we're trying to find the temperature. Good, that's good. We want 500. 500 keeps hitting around 500. 500. All right, so here's enthalpy right there. And what would we say? We want 2,890. 2,890. 2,890. It's somewhere in between 200 and 250. It's right in there. So, no, right in there. Somewhere in here. So here are the two values. Somewhere between, because we have 2,890, 2,855, 2,962, yeah, right in there. So we're going to use that and interpolate, and so our answer is going to be somewhere between 200 and 250. So I'll just draw my interpolation table. And over here, I will write my 200 and 250 right in there. Here's the value corresponding to 200 at that pressure is 2,855.37. And we have 2,960.68. The one we want is 2,890. And right here is the temperature that we have. So that versus that, that versus that. We can write this down as 2,855.3 minus 2,890. And then 2,960.68 minus, oops, I'm tied. Needs to be that minus that. And you say, well, it doesn't really matter, does it? Well, it's gonna you'll get the wrong sign, right? Because it needs to be consistent. Otherwise, the sign will be reversed onto the thing. So you can see that this is going to make it negative because I'm subtracting a bigger number from a smaller number. But I'm doing it in both this one and this one, so the sign goes away. If you notice that you do this left-handed side and the sign is negative, you did something wrong. And that's going to be equal to 200 minus t divided by 200 minus 250. And if you wanted to know this right here, I usually write it down, but not always, 0.6712. And the answer comes out to be 216.4 degrees Celsius. And boxed right in there. And now we got ourselves a 10-minute video. Any reflections to take place? I don't think so necessarily. You can see right here they're showing, there's a TH diagram. Let's see, we haven't introduced that yet. It exists. It's more common, I think, to have an enthalpy versus entropy, and when it comes to having an enthalpy diagram. But it exists. We'll go to another video for the next example.